All right. So just a reminder of what we went over last time. So we're talking about graphs, which are collections of nodes, vertices, and edges. So the vertices represent some objects, the edges represent some relationship. And so, for example, it could include the vertices being some committees and the edges being these two committees cannot meet at the same time. And so what we talked about last time was vertex coloring, where we assign each vertex a color such that we're operating under these two rules. So we want to use as few colors as possible, and we want to color each vertex such that no two adjacent vertices get the same color. We've got definitions to go along with that, where a proper vertex coloring is one where those rules are fulfilled, where we don't have the same assignment for two adjacent vertices. So like we cannot do something like color this one red and color that one red. That's not allowed. If we don't have that, then it's a proper vertex coloring. And if it has a proper vertex coloring, then we can say that that graph in general is K colorable, where K is however many colors we used. So for here, we used 3 colors, and so this graph is 3 colorable. And then furthermore, we say that the chromatic number of our graph is the smallest possible value that we can color it in with. So we talked about register allocation. Then we talked about the theorem for what sort of bounds can we have on that chromatic number, where if it has at least one vertex, then the chromatic number of the graph is at least 1, because there's at least one vertex to color. If there's at least one edge, then the chromatic number's got to be at least 2, because there's at least one edge, and so those two vertices can't be assigned to the same color. If the graph is complete, then it's got to be n, the number of vertices, because every vertex is adjacent to every other vertex. And so none of them can get, like, there's no color that can get repeated because the graph just doesn't allow for that. If we have a cycle, then it depends on whether our number of vertices is even or odd. If it's even, we can just split it down the middle and have 2 and alternate as we go around. But if there's an odd number, then we've got to use the third color at the last vertex as we're going around. All right. Then we talked about planarity, where if I have a map and I want to color in the map, then I want to know what's the fewest colors that I need to buy in order to make sure that each region of the map is colored, so each adjacent region doesn't get the same color. And so this is a simple coloring problem. It's also a planar graph. Yeah, question.
Does it work? How does it work with path graphs? Is there like a concrete method to do it with path graphs, or is it just
Okay, so that's a path graph. So let's color the first one red. And then we can color the next one purple. And then we can color the next one red. And then we can color the next one purple. And then we can color the next one red. Would have been better if I chose green. But yeah, so it's like cycle rules. Okay, so a path graph and this map type thing both are planar graphs, which means that we can draw them so that no edge overlaps. And so this path graph on 1, 2, 3, 4, 5, 6 vertices is planar because we can draw it and that none of the edges are overlapping. And we have a theorem which we call the four-color theorem, which says that if G is planar, then its chromatic number is at least 4. In terms of how we would prove this, this is like, it's one of the interesting stories of computer science and mathematics where so like this was a very famous theorem that went unsolved for many years, and then someone like plugged in all the possible configurations into a computer and then was like, here, I've shown that any possible configuration of a planar graph, the chromatic number is at least 4. And people were like, what? What? Does that work? So it's more of a computational proof than an actual like proof style proof. Um, and so nowadays people are like, yeah, okay, the four-color theorem is true. Um, I don't think anyone's ever really beaten the computational proof though. Okay, so I want to have a few minutes for you to practice with homework questions because we've talked a lot about like what are graphs, but not so much about like how do you actually solve a problem that you're going to be asked to do it on the homework. So I'm going to put you into groups and have you work on these. And let's say for each one that you solve, come up and I will check your answer just to make sure that you don't get too far off the right track. All right, so these are a selection of homework problems. So I start with 9.1. Move that one up. I've selected some from 9.2 and 9.3. And so we'll spend maybe 20 minutes doing this and then we'll talk about trees. All right, so we'll talk briefly about trees today. The goal is to talk about some definitions and then we'll talk about spanning trees next time. I'm hoping to have more time to work on homework questions as well. Okay, so what's the definition of a connected graph? Right, so nothing gets isolated, so no isolated vertices. Another way of putting it, yeah. Every edge possible is present. No, that's a complete graph. Think about path. So a connected graph is when there is a path between every pair of vertices, which does mean that there's no isolated vertices. So whatever vertex is in our graph, we can go from any one to any other. That's a connected graph. I want to mention a kind of graph which we call acyclic. So for example, this is a graph. This graph is what we call cyclic. Can you guess why? There's a cycle in there, isn't there? So there it is, where we can start at one vertex, go around and reach the other one. So that graph is cyclic. Let's consider this graph. Is there a cycle in that graph? In fact, there is not. And so when there is no cycle, when there is no subgraph of a cycle in a graph, then we say that the graph is acyclic. when no cycle is a subgraph. So no cycles allowed. And then we say that the graph is acyclic. All right. So when we want to talk about a tree is a graph that is both connected and acyclic. So this is a connected and acyclic graph. This graph here, that's a tree. It's connected, it's acyclic. This graph is not a tree. It is cyclic. What if we have, okay, so if it's cyclic, then it's just not a tree. What if we had something like this, where this is assumed to be our graph? It's not connected, so it's not a tree by our definition. It is acyclic, but each of those components happen to be trees, right? So that's a tree. That's also a tree. I'm so excited. These names are amazing. So because this disconnected acyclic graph contains trees, we call it a forest. Because there's trees in there, it's just disconnected. When it's a disconnected acyclic graph. Okay. Let's look briefly at some examples. All right. Nope. Meant for that to be the other thing. All right. What is this? Yeah. Tree? Yes. What about this one? Also a tree? Yep. Connected, acyclic. What about this one? One that looks like an A. It's not a tree. So what is it? A forest. And what about this one? Yeah, it's cyclic. So it's not a tree, nor is it a forest. So tree, no. Forest, no. Okay. Got a theorem for you. Theorem 9.9, which says, let G be a simple graph on n vertices. Then we say if G is connected, we're trying to say something about the number of edges. It has at least n minus 1 edges, which we know the simplest possible way to express that would be a path graph, which we know has n minus 1 edges. The other case here is if G is acyclic, it has at most n minus 1 edges. Because we cannot link back to any other ones. So we can't have more than n minus 1 edges. Because no cycles are allowed. What does this tell you about trees then? How many edges do trees have? Yeah. N minus 1. Exactly. Because we are bounded both at the lower end by it being connected. We're bounded at the upper end by it being acyclic. And so since trees are both acyclic and connected, then we can say that this is corollary 910, which is any tree on n vertices has exactly n minus 1 edges. There's another corollary, which I think it just restates the things where any two of the following will imply the third and yield that G is a tree, where the first is that the number of edges is n minus 1. The second is that G is connected. The third is that G is acyclic. So any two of those imply the third. So if the number of edges is n minus 1 and it's acyclic, it's a tree. The number of edges is n minus 1 and it's connected, it's a tree, and so on. So we've got 3 statements. Choose 2 of them. I'm telling you, combinatorics comes in everywhere. All right, so the next set of definitions we've got are all about direction. So remember way back when I said if we have, so like, let's say that this is person 1 and this is person 2, and if they follow each other on Instagram, then person 1 follows person 2, so there's an edge there, and like with an arrow, so person 1 follows person 2. And if person 2 follows person 1 back, we have 2 ends to the arrows. And then this is what we just draw as an undirected graph, to assume that these links go both ways. If we chose to work under the paradigm where, like, if person 2 was famous, then we have only a lot of people follow person 2, but they maybe only follow a few people back. Then this is what we call a directed graph, which is where we do not assume that the edges go both ways. We assume that we're going to draw the arrows, and then that carries meaning for the graph. So to do this for trees, we apply this and we say that a directed tree, let's read the book definition. A directed tree is a digraph, directed graph, that contains a vertex V naught called the root of the tree, for which there exists a unique path from V naught to every other vertex. It's basically a tree that we draw with arrows. And so we have some vertex, which the book calls V naught, V sub 0, and we call this the root. So this part is going to use a mix of like botanical language for things and also like family tree for things. So that's where we get this sort of notion. And so from V naught, we can draw arrows. And so V naught is the root, and then we go down the tree and okay. So let's assume this is let's call this A. And we have something like this, where we go from A to B. We call A the parent, we call B the child, This is where the family tree naming stuff comes in. If a parent has more than one child, then they're all called children. Any guess what these are called in relation to each other? Siblings. Let's assume that there's some path. So let's say this is, let's call this vertex X. So X we can get to from V naught. And so we can say that X is a descendant of V naught, because from V naught we can find a path all the way down to get to X. Okay, so we've got root, we've got parent, we've got offspring or children, we've got descendant, siblings, we've got leaves. So we've got the root and then we've got leaves. If you think of a tree, like the root is at the bottom. So if we take this tree and like flip it upside down, and then it grows up, it's got branches, and then at the very ends of it are leaves. Those are the end. Like the tree doesn't go beyond that. And so we say that like that's a leaf. That's also a leaf. These are also leaves. That's not a leaf because it has a descendant. This is also not a leaf because it has descendants. But the things that don't have any outgoing edges are called leaves. All right, the other thing is the notion of level. So if we draw a tree kind of like this, where we've got the roots at the top, and we organize it in this way. Remember, for graphs, it doesn't matter how we draw things. So we're imposing some sort of structure on the way that we draw this graph. But we've chosen a vertex that has no, so when we talk about degree as like the number of edges associated with a vertex, there's, so like the degree of this vertex is 1. If we add arrows to the mix, then there's this notion of an out degree and an in degree. And so like for this vertex, the out degree is 1. The in degree is 0 because there's nothing coming into that vertex. So there's no arrow that points in. For the other one, there's no out degree, but there is 1 in degree because there's an arrow coming in there. So the root is just whatever vertex that doesn't have an in degree. And so when we order it and we draw it like this, so we start at the root, we've got levels to this graph where each row of descendants is a new level. So that's a level, that's a level, and that's a level. This is order that we're imposing on this graph. And so the level of a vertex in a tree indicates the length of the unique path from the root to that vertex. So if we think of this vertex down here, it took us 1, 2, 3, a path of length 3 to get from the root to this very bottom vertex. And so we say that this vertex is on level 3. Length of unique path to a vertex from the root. And so when we talk about how many levels do we have, when we say, when we're looking at like the maximum number of levels, so like the level of this vertex over here is 1, 2. But if we're talking about the maximum number of levels that we have in the tree, it's 3. This is assuming that the root is at level 0. And so we say the height is just the maximum level. And so we say that this tree has height of 3 because there's 3 levels. All right. Okay, so we call these types of graphs, so this is all about directed graphs. We can have a tree like this and still use that terminology without the arrows. So like, where did I draw it? So like, this is still a tree. We could just decide one of these vertices is the root. So like, we could decide that vertex is the root. And then we say it is a rooted tree. We could alternatively decide that that vertex is the root. It's still a rooted tree. It's just some order that we've imposed to say, I'm picking that one, that's the root. And then we go on with our day. Yes, question.
If you were to do the vertex on the bottom left of the tree, like the one at the very end, the straight line, yeah. Which way would like the height levels go? Like would it go? Can there be other things on the same height as the root or same level as the root?
Nope. So we would draw it into. I think that's how we would draw it. And so we would say it has 1, 2, 3, 4 levels. Again, this is just order that we're imposing on this graph. We've arbitrarily chosen one of the vertices to be the root, and then we just draw it this way so that there are levels. Let's go back down. And so we say any tree where we designate a root. All right, there's a notion of a binary tree, which, okay, so binary is 2. And so there's going to be 2 of something, and it ends up being the requirement that each vertex has at most 2 children. So that looks like, so if this is the root, then each vertex has to have at most. So it could only have 1. It could have none. But it can have only at most 2. It can't have 3. All right, so we're out of time. So we will resume with the complete binary tree, and then we'll talk about spanning trees and all that fun stuff on Friday.